Hi there, my name is Rishabh Singh, and I'm going to be giving a brief presentation on my topic of PhD research, where we utilize the reproducing kernel Hilbert space and some aspects of quantum mathematics to come up with a very precise framework for uncertainty quantification for both data and learning models. So the objective of our work is fairly straightforward. We develop a framework for multi-moment quantification of uncertainty for data and learning models. The motivation for doing so stems from two different aspects. One is machine learning and the other is feature engineering. When it comes to machine learning, we know that deep neural network models are the predominant choice today for almost all pattern recognition tasks. However, these models are highly vulnerable to poor performance due to poor choice of architecture or training parameters or lack of sufficiently labeled training data. Furthermore, these models are also very susceptible to adversarial attacks and distributional shifts in test data when they are deployed. This makes the quantification of performance trustworthiness of DNNs very vital, especially in safety critical applications such as healthcare and autonomous vision, where one cannot afford to make a mistake. This is where we think that an efficient uncertainty quantification framework can be really useful in determining the performance trustworthiness of such models, because they can tell us exactly how much to rely on a prediction made by a model. On the other hand, in feature engineering, and specifically we talk about time series data analysis, we realize that pattern recognition tasks for such applications is still very challenging. And this is because mainly due to the non-stationary nature of real world time series data, and also due to corruption of data sets due to statistical drifts, anomalies, and noise. Here again, we think that a sensitive multi-moment uncertainty quantification for data can be very useful in identifying or detecting such situations of statistical drifts and anomalies, and thereby be very useful for general purpose data analysis and time series applications such as unsupervised clustering, anomaly detection, dependency quantification, and surprise novelty quantification, etc. So when we look at current methods in uncertainty quantification in machine learning, we realize that most of them are related to Bayesian and ensemble techniques. And these techniques are infamous for being highly iterative and therefore computationally expensive to implement in practice. They do not scale well to larger models and data sets. Furthermore, Bayesian and ensemble techniques are also limited to extraction of only central moments of uncertainty, thereby not providing a very precise estimation of uncertainty. And due to this reason, they also fail to capture a model's true posterior predictive PDF, especially in high dimensional problems. On the other hand, when we look at data feature engineering techniques, we see that there are very few techniques that perform meaningful statistical decomposition of data in a computationally efficient manner. Specifically, they fail to characterize the tail regions of data PDF, which is actually very important for anomaly detection, drift detection, and also for dependency quantification, especially in the finance application domain. Furthermore, these techniques are not sensitive to local dynamical changes of data, further putting them in a disadvantage when it comes to time series analysis, especially in non-stationary case. So these are the limitations in the two broad fields that we try and address with our framework of multi-moment uncertainty quantification for both data and models. So the key aspects of our framework are as follows. We basically implement a moment decomposition of the local gradient flow of the data PDF, that is the probability density function. And this results in an unsupervised clustering of data based on its uncertainty. So this is the working principle of our framework. And there are two main components to it. One is the reproducing kernel Hilbert space, which we use to quantify the data PDF. And the other are certain formulations from quantum mathematics, which we use for quantifying the gradient flow of the data PDF, particularly in terms of multiple local moments that essentially quantify the uncertainty of the data. To illustrate on this, let us consider the simple case of a sine wave. We know that the PDF characteristics of a sine wave look something like this, consisting of two peaks, where each peak corresponds to the positive and negative amplitude peaks respectively, where the sample density is the highest. What our framework does is that it works on the local gradient flow of the data PDF characteristics. Particularly, it performs a moment decomposition on the local gradient flow of the data PDF in such a manner that the higher order moments that are extracted quantify the tail regions and the locally heterogeneous regions of the data PDF. And this essentially leads to an unsupervised clustering of the data space in such a way that the successively higher order moments signify the more uncertain regions of the data space, because those are the regions corresponding to the tail regions or the heterogeneous regions of the corresponding data PDF, where the sample density is low. So there are many advantages of our framework. First and foremost, the uncertainty quantified by our framework is functionally defined thanks to the use of the reproducing kernel Hilbert space. And hence we require no iterative procedures for estimating it. And because of this, our framework has a very low computational overhead, and it is able to scale better to larger models and data sets. Furthermore, due to the fact that our model our framework extracts multiple local moments of uncertainty, it provides a very high resolution and more precise estimation of uncertainty in terms of specificity and sensitivity. Moreover, since the moments are self-organized very systematically in such a way that successively higher order moments quantify the more uncertain regions of the data space, our framework is more interpretable in terms of uncertainty when compared to Bayesian and ensemble techniques. So the key components of our framework are as follows, and I briefly touched upon them in the previous slide. These are the reproducing kernel Hilbert space, which is a well-known tool in data analysis, and operator theory, which is a well-established tool in quantum mathematics, and particularly in quantum physics, where it is used for describing the dynamics of physical systems, such as particles in a field. So we use the RKHS for quantifying the data PDF, and we use operator theory for quantifying the local gradient flow of the data PDF, particularly in terms of a number of local uncertainty moments. So the RKHS basically provides a mathematically rigorous functional representation of nonlinear patterns in input data. One can infer nonlinear deterministic functions using linear computations in the RKHS, and this provides a very good alternative to using stochastic iterative methods to infer such nonlinear functions. Furthermore, thanks to the representers theorem, computations in the RKHS directly map to the desired function space. And in our case, the desired function space is going to be the space of data uncertainty. On the other hand, operator theory provides a very good description of local dynamics and anisotropy of physical systems, particularly particles in a field. Quantum mathematical formulations are also well known for describing physical systems in terms of multiple moments of their dynamics and uncertainty. We can therefore see how such formulations can be very useful for our goal of data uncertainty quantification. One of the significant aspects of quantum mathematics is that most of the formulations operate in the Hilbert space. This is because most of the systems in quantum physics are described stochastically as Hilbert space, as finite Hilbert space formulations. And this is very advantageous for us because we can essentially replace the Hilbert space with a data-defined RKHS to thereby use all of the advantages that quantum mathematical formulations have to offer, but for data analysis and specifically uncertainty quantification of data. And that is what we do through our framework. We provide a very elegant and natural link between quantum mathematics and data-defined RKHS to eventually come up with a very precise and sensitive framework for uncertainty quantification. So the overview of our framework is as follows. We start with the input space, and the input could be anything. It could be a time series signal, it could be a set of images, or it could be a set of trained weights of a neural network model. Our first step is to project the input data into an RKHS using a metric that quantifies the PDF of the input data. And then we use, in the second step, physics-inspired operators, particularly Laplacian-based operators, to quantify the gradient flow of the data PDF or the input space PDF. And here we particularly make use of the Schrodinger's equation formulation related to these operators, with the RKHS metric defining the data PDF as the wave function in the Schrodinger's equation. And so here what we are essentially doing is treating the data PDF space as a physical system on which we impose some quantum mathematical formulations to extract precise uncertainty moments. And that is what we do in the final step. We solve this data-defined Schrodinger's equation to extract various moments of local uncertainty and eventually attain a continuous multi-moment uncertainty landscape associated with the input data. And here at each point of evaluation is basically defined by several moments of local uncertainty, which intrinsically quantify the variability or the dynamics of the input space in the local neighborhood of the point being evaluated. So this is the abstract overview of our framework for uncertainty quantification. Specifically, we focus on model uncertainty quantification for most of our work, and therefore the input data in our case is a set of trained model weights, which we project into the RKHS and then implement gradient flow operators in a similar way as I described in the previous slide to eventually obtain an uncertainty landscape associated with the weights of the trained model. And in this landscape, when we evaluate a model output or a prediction, then what we essentially gain is output local uncertainty moments associated with that prediction, which intuitively quantify the local variability of the weight space or the local dynamics of the weight space in the neighborhood of that point of evaluation. Now, to describe our goal more concisely, we set up the problem formulation as follows. Let us consider a given neural network that is being trained on a dataset consisting of n IID samples, where the training input is in a d-dimensional real space and is denoted by xi, and the training desired output is basically a k-dimensional categorical variable and denoted by yi. Test input is denoted by xi star and test output is denoted by yi star. So now our goal is to come up with an uncertainty quantification formulation that is basically a pseudo measurement of the posterior predictive PDF of the model at a test output, given the corresponding test input and given the trained set of weights of the neural network model. So we denote this uncertainty quantification framework as h of psi, and we call this a pseudo measurement of the posterior predictive PDF because we are not aiming to exactly estimate this posterior. But instead, what we are trying to do through our uncertainty quantification formulation is estimate precisely the local variability and the local dynamics of the posterior PDF in the neighborhood of the point of prediction being evaluated on. So that would essentially give you a very precise estimation of the uncertainty envelope around the prediction points. And that is how our framework principally works. So now the traditional way of formulating model uncertainty has always been the Bayesian interpretation, which consists of an inference problem where we need to determine the posterior distribution of the weights of the model given the training data set. And this is actually very difficult to determine because of the computationally intractable marginal likelihood term that you see over here. So most of the existing methods try to come up with faster approaches of determining this posterior. Now, during the prediction phase, the uncertainty in this formulation is quantified by estimating the posterior predictive PDF of the model corresponding to any unknown data pair in the test set, which is formulated as follows. So here you can see that the posterior predictive PDF involves a marginalization problem over the weights of the model. And therefore, even during the prediction phase, the estimation of uncertainty is computationally intensive because we have to search over or scan over the entire weight space of the model. And this usually involves iterative procedures in these methods to approximate the posterior predictive PDF. That is, various iterations or various realizations of the model. Our interpretation of model uncertainty is significantly different from the Bayesian approach. What we want to do is estimate very precisely the local dynamics or the local variability of the posterior predictive PDF of the model at any prediction point, given the corresponding input and given the trained set of weights. So we are basically working with a point prediction model that has already been trained and we have access to its weights. So our first step is to project the weights in an RKHS, which basically give you the intrinsic density characteristics or intrinsic PDF of associated with the weights of the model. And then we evaluate the model output in that data PDF formulation or the weight PDF formulation in the RKHS. And this we treat as an initial rough approximation to the posterior predictive PDF whose dynamics we are trying to quantify. Our second step is to basically quantify the local gradient flow of this RKHS metric that quantifies the PDF of the weights. And by doing so, we closely approximate the local dynamics or variability of the posterior predictive PDF of the model. And using quantum mathematical formulations, we specifically decompose the local gradient flow in terms of many local moments. And these basic moments basically give a far more precise estimation of the local variability or the local dynamics of the posterior predictive PDF. And this is how we attain many local uncertainty moments that increase in sensitivity as we go to higher order modes associated with the model, specifically with the model weights. So now we give a slightly different interpretation of how our approach is different from the Bayesian approach. The Bayesian approach involves a forward viewpoint where iterative procedures are done to quantify the intrinsic variability of weights at the output. And that is how the uncertainty is quantified associated with each output. In our approach, the viewpoint is reversed. That is, we quantify the intrinsic variability of weights functionally first, and then we evaluate the output in this functional that basically defines the variability of weights. And that is how the variability of weights is quantified at each point of evaluation, and that is how we quantify the uncertainty. So this is how our approach for uncertainty quantification differs from that of Bayesian approaches. So now we delve a little into the technical aspects of our framework. The particular metric that we use to project the input weights into the RKHS is called the information potential field. And this is basically a functional measure of data PDF in the RKHS formulated as shown. This is basically just a Parson window estimate of the PDF in the RKHS, and it gives us an asymptotically unbiased PDF estimate. It is also related to the kernel mean embedding. It is basically its empirical approximate and therefore has a lot of powerful statistical properties as a PDF estimator. So we use the information potential field or the IPF to first estimate the PDF of the weights of the model. The second step is to construct a Schrodinger's equation over the IPF of the weights. And this is done to quantify the gradient flow of the weight PDF. So the Schrodinger's equation is formulated as follows. It consists of a Hamiltonian term, which is basically a set of operators that is used for gradient flow, for quantifying the gradient flow of the IPF. And this Hamiltonian overall basically measures the rate of change of the system, where the system is basically the IPF that measures the probability at any given point of evaluation. Here, the E term over here denotes the eigenfunctions over the IPF or the energy levels over the IPF. Our final step is to solve this Schrodinger's equation to extract the corresponding local moments of uncertainty. And to do that, we particularly use perturbation theory. I wouldn't delve into the details of how exactly we do this, but it basically involves perturbing the system to shift the evaluation from y star to its neighborhood. And so therefore we use a perturbation Hamiltonian that is basically the Laplacian Hamiltonian, which is what basically shifts the evaluation to basically study how the system behaves in its neighborhood, how the IPF changes in the neighborhood of the point at which it is being evaluated on. And that is the working principle of perturbation theory. And using this, we basically obtain what is called the quantum IPF. And quantum IPF is basically a set of local uncertainty modes that we attain corresponding to the IPF being evaluated at any particular point. And it is basically a function of the local gradient flow of the IPF and normalized by the IPF itself, as well as the kernel width that is used to construct that IPF. So the K here basically denotes the moment index of the local uncertainty moment. So eventually what we gain using the QIPF or the quantum IPF are basically the successive uncertainty moments evaluated at any particular model prediction y star. Now we go back to the sine wave example to illustrate how the modes behave. And we see here that the QIPF mode 1 expectedly quantifies the region around the peaks of the PDF of the sine wave. And as you go further, you will notice that the successive order modes quantify the more tail regions of the sine wave PDF, and they actually cluster around the tail regions of the IPF. Now we move on to some results, and we start off with some illustrative examples related to both regression and classification. So we start off with a regression example where we train a 3 hidden layer neural network model on 120 regression points that are synthetically generated and are added with noise. So those training data samples can be seen here as the red dots. And the model is basically evaluated over the entire data space, including in regions which the model has not seen during training, that is the pink band regions. And then the uncertainty is quantified using many different methods, that is QIPF, stochastic gradient descent, stochastic weight averaging using Gaussian, and Monte Carlo dropout. So here we see that the uncertainty bands quantified by the QIPF is more sensitive in detecting regions outside of the training data set than all of the other methods, and which is basically the ideal behavior of how uncertainty estimate should behave in this case. Furthermore, we see that the moments, the local moments of the QIPF, that is, are more interpretable. That is, as you go to the higher order moments, you see that they are more sensitive in quantifying the uncertainty as you move away from the training regions. That is, you see that here mode 3 is the most sensitive towards where the model is being evaluated as compared to mode 2 and then mode 1, etc. That kind of an interpretability is not seen in all of the other methods, which simply give you only the mean and the standard deviation of the uncertainty bands, which are basically the central moments. So, and we do the same kind of an analysis for the classification, where we have 2 moons data set with added noise, and we train a similar neural network to identify the decision boundary, and we evaluate the network on the entire data space and quantify uncertainty using the different methods. We see here that the QIPF is much more sensitive than all of the other methods in quantifying the uncertainty at the decision boundary. It is able to separate out the decision boundary in terms of uncertainty very sharply from all of the other regions of the data space. It displays confidence only in the thin strip of regions where the samples are present. And as you move away from the training samples, the uncertainty, according to the QIPF, increases drastically. And this kind of consistent behavior in the uncertainty is not seen in all of the other methods, where sometimes the uncertainty pattern is very arbitrary and there is no identification of the decision boundary in terms of uncertainty. And here we show more examples where it is seen that the QIPF framework is robust to outliers in the training set as compared to Gaussian process regression and Monte Carlo dropout. And then Here we basically measure the closeness of the uncertainty quantification measures with the prediction errors in the test set when the model is trained using various benchmark UCI regression data sets. Here we see that the QIPF uncertainty estimates more closely correlate with the prediction errors than MC dropout. One of the ways to evaluate the quality of an uncertainty quantification framework is by evaluating its ability to separate out correct predictions from the wrong predictions of a model when it is being tested. And that is what we show here in the case of a LeanNet model trained on KMNIST dataset. We basically evaluate the histograms of uncertainty estimates corresponding to correct predictions, that is denoted by blue, and corresponding to wrong predictions, that is denoted by pink. And then we compare the histograms of the two for each of the uncertainty quantification methods. And we see here that the QIPF is able to really separate out the distributions of the uncertainty estimates corresponding to correct and wrong predictions more efficiently than all of the other methods. And this is also evident from the error detection performances of the different uncertainty quantification frameworks, where we see that the QIPF framework is able to, according to the receiver operating characteristics and the precision recall characteristics, the QIPF is more precise than other methods in detecting model errors during testing. And we perform similar evaluation and comparison of the different uncertainty quantification methods when the test set undergoes a distributional shift, more specifically a covariate shift, where its governing PDF undergoes a shift so that it's not the same as the training PDF, but the target conditional remains the same. And we do this using various corruption techniques, that is in the tests, that is rotation, shear, zoom, and shift. And in all of these cases, we see that the error detection performance of the QIPF remains much better than all of the other methods at every corruption intensity. In this case, the corruption method is rotation. And we see here that in both ROC AUC and PR AUC, values of the QIPF remains higher than other methods in all of the corruption intensities. And the same is shown for shift corruption as well. The QIPF is much better than all of the other methods in detecting the errors, even when the data set undergoes a covariate shift of varying degrees during testing. Another way of evaluating the quality of an uncertainty quantification method is by seeing how well calibrated the uncertainty estimates are with respect to the model error in the test set. So by calibration, we mean that the uncertainty estimates should increase proportionally, basically in proportion with the number of errors that the model makes. And that is what one of the metrics called the expected calibration error measures. So the lower the ECE value, the more calibrated the uncertainty quantification method is. And we see here that the QIPF is much more calibrated than all of the other methods in different intensities of distributional shift during the test set. And another way of judging the UQ method is by simply measuring the correlation with the model error. And in this case, we take the error point biserial correlation metric and measure this correlation at different distributional shift intensities of all of the uncertainty quantification methods. And we see that the QIPF remains more correlated with the error than all of the other methods. And here we basically summarize the average error detection capabilities in terms of ROC AUC and PR AUC, average ROC AUC and average PR AUC values of all of the uncertainty quantification methods for detecting errors on various different data sets and various different models as well for many different corruption types during testing. And we see here that the QIPF dominates over all of the other methods in most of the cases. And the same kind of analysis is made in terms of expected calibration error and Breyer score, which is also another calibration metric. So here the lower values are better, and we see that the QIPF is, if not the best, is at least the second best, compared to all of the methods. And when we talk about computational complexity, the QIPF computational complexity increases linearly with the number of weights and the number of extracted moments. However, one key aspect here is that we do not use all of the weights in practice. In fact, in all of the results I showed before, we have definitely not used all of the weights. We have heavily downsampled the weights to decrease the effective value of n considerably. And so the effective computational cost of the QIPF remains very low. And this is evident from the per test sample time taken by each of the uncertainty quantification methods for different models, such as LeNet, VGG3, and ResNet-18. We see here that the QIPF takes much lesser time than Monte Carlo dropout. In fact, an order of magnitude less time than Monte Carlo dropout, and achieves similar results as shown before. We also evaluate our framework in the case of transfer learning, where the IPF field is formed by the source model, by the weights of the source model, and the weights of the fine-tuned model are evaluated in this field to quantify the average uncertainty of the fine-tuned model with respect to the source model. And we do this for at least 50 different UCI time series datasets. That is, we take each of these datasets as a source dataset and fine-tune it on all of the other datasets and measure the average test set error. And we see here that the average uncertainty estimate of the QIPF in each of these cases is very closely correlated with the actual average test set errors, as is evident from the correlation coefficient here of 0.85, which is pretty high. And this is just another example of uncertainty quantification using QIPF in the case of transfer learning, where the source data set was ImageNet and the target data set was KMNest. And we see here that QIPF performs much better than Monte Carlo dropout in the error detection in that case. Now, another major application arena where we utilized and compared the various UQ methods is the semantic segmentation problem, where a neural network is basically trained to give out a segmentation map corresponding to the different images. And those segmentation maps in this case can be that of road scenes, where the model is trained to discriminate, basically classify different objects into different segments like sidewalk, pedestrians, buildings, roads, etc. And so what we want to do here is basically quantify how uncertain the model is in segmenting or in giving out segments. So here we evaluate the UQ framework as follows. So let us consider a network that has been trained to segment any given input frame. So we feed the input frame to the network and we get out the predicted segments corresponding to the network. We have the ground truth segments, and using the ground truth segments, we measure the difference between the predicted segmentation map and the ground truth segmentation map and come out and eventually attain the segmentation error map. And at the same time, we also quantify the uncertainty, pixel-wise uncertainty, using the different UQ methods. And we judge the quality of the uncertainty estimate by correlating it with the segmentation error map. So the better correlated it is with the error map, the better the quality of the uncertainty estimate is. And that is what we do with the QIPF as well. We basically extract pixel-wise uncertainty using the QIPF framework, and we do segment-wise averaging to finally obtain the uncertainty of the model at each segment that it predicts. And we do this for several segmentation architectures for two different major data sets that classifies road scenes in terms of segments. And basically what we see in this demonstration is that the segment-wise QIPF uncertainty is highly correlated with the segmentation error map. And this is for the case of the CAMVID dataset, the test set of the CAMVID dataset, which is basically a high ideal behavior. You see that the uncertainty for sidewalks and pedestrians is high, and the errors for the segmentation error of the model is also high corresponding to that, which is basically a very good indication of how well the QIPF is able to quantify the uncertainty. We evaluate the UQ methods for semantic segmentation uncertainty quantification using several metrics, such as the probability of a patch being accurate given that a UQ method has classified it as being certain, and the probability of a patch being uncertain according to a UQ method given that it is inaccurately segmented by the model. And then we also combine those two to come up with another third metric. So all of these metrics should ideally be have higher values for better uncertainty estimates. And we see that for different thresholds, the QIPF is much better in terms of those uncertainty metrics. In this case, for FCN8, where each of these metrics is much higher for QIPF than all of the other methods. And similarly for SegNet also, the QIPF performs much better than all of the other metrics. And we did this for 4 different models, and in all of the 4 cases, we see that the QIPF performs much better and detects accurate and incorrect segments much more accurately than all of the other methods. And this just shows the error detection performance of the QIPF, which also is high in the traditional sense of receiver operating characteristics and precision recall characteristics. So that concludes the model uncertainty part of my work. Some other applications that I have some preliminary results on are some time series analysis applications. And this includes dependency measure where we combine the QIPF uncertainty framework with optimal transport as a measure for dependency between different time series signals. And some other applications that I have some results are for implementing QIPF for unsupervised clustering, change detection, and surprise quantification. So for time series analysis using QIPF, the framework is basically the same, except for that instead of model weights, you have the data corresponding to the time series data that you project into an RKHS field and then implement functional gradient-based operators on them to come up with a data uncertainty landscape where a new sample gets, where a set of modes is associated, uncertainty modes is associated with any new sample that we encounter in the time series data. So we use this for change point detection as well. And using the QIPF framework, we have shown that we can efficiently detect change points in a given data set using some synthetic change point generators. And we see that the QIPF is much better than some traditional Bayesian change point detection methods and KL divergence space metrics. And also for optimal transport or for dependency measure, we combine QIPF with optimal transport. And we have shown that such a method leads to a consistent behavior of dependency measures with different degrees of dependence as compared to other methods. And we have also carried out experiments using the QIPF to decompose dependencies between different variables. Here we quantify, we also make use of optimal transport methodologies. Basically, we decompose the distributions of the two different variables using the QIPF. And then we carry out a mode constraint optimal transport between the sets of decomposed QIPF modes corresponding to the two variables. And we show that, quantifying dependency between two variables in such a way leads to a more consistent or an equitable behavior with respect to different degrees of dependencies as compared to other methods such as Pearson, Spearman, Kendall, and Coppola optimal transport-based methods. So that concludes my work during my PhD. There are a lot of possibilities of how this work can be carried out in the future. These are just some ideas, but they are not exhaustive at all. And these are some publications related to this work. This is the latest paper, which is under review at IEEE TPAMI. Another one is published in Neural Computation and another in UAI 2020. There should be another one up in progress, which should be done by the end of this term. And then there are some other conference papers, and these are some publications related to other topics that I got involved in through my PhD career. So that marks the end of my presentation. Thank you so much for listening. And if you have any contacts, feel free to, if you have any questions, feel free to contact me. Thank you.